Okay, welcome back. We have a lot to cover today. I'm going to try very hard not to run over because I finally got a vaccine appointment and I don't want to miss it. So I'm going to be dashing out of the house at the end of class. It's going to be at the fairground, Santa Clara County Fairgrounds, and that's my first COVID shot. So we'll see how it goes. Okay. All right. We're going to talk a lot about processes today. And as I've mentioned before, processes are very important task for operating systems because processes are running programs, and that's what we rely on the operating system to do for us, is to run our programs. Now, when I left off last week, okay, well, first of all, remind you, a process is a running program, and a process runs in its own address space. Now, that's a very important concept. When you run a program, the operating system allocates a certain chunk of memory for your program to run in, and that's known as the address space of your program. Okay. Now, when we left off last Friday, I started talking about threads. Okay. Now, on the left here, you see a process, and it's running one thread. A thread is a path that controls your program. So your program is executing and control is going through your program. That's a thread. Okay. Now, on the right here, you see that it's possible to have a process spawn multiple threads. Okay. And so here on the right is a single process, but there are 3 threads running through it. Okay. And the thing to know about threads is that because they're all running within a process, the threads are sharing code, data, any files that may be open. Okay. Now, each thread will have its own runtime stack and its own copy of the registers, but otherwise, memory is being shared. They're all running in the process's address space. Okay. At the end of the lecture, we'll look and see how we can actually start these threads, how they have to coordinate with each other, and that will lead into next week when we do a lot of looking into multi-threaded programming. Okay, but I wanted to sort of set the stage for that. Okay, terminology. Now, when we're talking about processes, remember we forked a child process. Okay, so that's the terminology. A process can fork another process, and remember, when we fork a child process, it gets a copy of the parent process's memory. Okay, but it does. The child process is running in its own address space, which starts out as a copy of the parent's address space. Okay. Now, when it comes to threads, the term is spawning thread, S-P-A-W-N. So a process can spawn multiple threads. And as I said earlier, all these threads are running in the same address space, okay, the address space of the process. So that means we have to put a lot of work into coordinating these threads so that they're not stepping all over each other. You don't want 2 threads to be modifying the same array at the same time. Okay, so things like that. Okay, so we'll get to those issues later in the hour. Okay. All right. Let's go back to talking about processes. Okay. If you have multiple processes, they could be independent processes, meaning you started them up independently. It could be two programs that you're running, or it could be a parent-child relationship, such as a process that forked the child process. In any case, you do have multiple processes running, and how do these processes communicate with each other? And maybe you have an application that is consists of several programs that you start up, and these programs have to talk to each other. Okay, and so if they're talking to each other, then you would say, well, okay, then they're cooperating with each other, and a cooperating process can affect another process or be affected by another process. Okay, if the processes are truly independent, okay, that means that they're not cooperating. You started up these different processes, two different programs, not a parent-child relationship. They're totally separate programs. They don't affect each other. Okay, so what we're going to be concerned about are the processes that have to coordinate with each other. Okay, so cooperate with each other. Okay, so let's see how the operating system provides mechanisms for programs, for processes to talk to each other. Okay, now why would we want to have cooperating processes? They can share information. If multiple processes are working together, it could make things go faster, computational speed up. A modularity, it may be a very good idea to break up your application into separate programs. And it is convenience for programmers. You can write these programs, test them separately, and then put them all together into an application and have the processes cooperating with each other. Okay? So there are multiple reasons why you would want to have cooperating processes, and we will rely on the operating system to give us the mechanisms to allow them to cooperate. Okay? So the term is inter-process communication, or IPC, and it's all about exchanging data and information. Okay? Now there are two models of inter-process communication. There's shared memory, where there's a chunk of memory that has been allocated, and multiple processes have access to that shared memory. Okay, and then there's message passing, where one process can send a message to another process. Okay, and that's the message passing model. Okay, now the shared memory is interesting because normally when you run programs, they each live in its address space, and of course they don't interfere with each other. One program is not allowed to write into the address space of another program or read from the address space of another program. The operating system tries very hard to make sure that a program lives within its address space. Okay. Shared memory is when two programs agree to share some memory that they allocate, and they can both read and write in that shared memory. Okay. So, if one process writes something into the shared memory, the other process can read it, okay? And vice versa. Okay. All right. So here's a diagram of the two ways. Shared memory. Okay, so here's process A in its address space. Here's process B in its address space, and they allocate some shared memory, and they can both access that shared memory. Okay, here is message passing, and we have process A and B, and thanks to the operating system, we've set up some a message queue, and okay, it looks like process B could be writing messages, and process A could be reading the messages. Okay, and the messages are going through this queue. Okay, I'm going to show a number of example programs, and I have posted these programs so that you can play with them at home. But I want to describe the concept and then show a simple program that actually implements that concept using POSIX calls. Okay, I'm going to try very hard to limit my programs to making POSIX calls so that you can compile and run them on different platforms. Okay, okay, let's talk about shared memory. Okay, so cooperating processes, okay, establish a shared memory region. Okay, I'm going to limit my examples to 2 processes for now, but you know, it can be more than 2. Okay, so once this shared memory region has been established, okay, all the processes will treat that shared memory as regular memory. Okay, so each process will treat that shared memory, as if that memory were in its address space. Okay, because of that, once the shared memory has been created, yeah, we do need the operating system to allocate it for us. But once that shared memory has been allocated, the operating system has no more work to do. Each process accesses the shared memory as if, just like regular memory, and so the OS doesn't really have to do anything. Okay, therefore, this is the most efficient and the most convenient way of having interprocess communication. It's faster than message passing. Okay, and now typically what happens is that one process will go ahead and create the shared memory, and so that shared memory will be in the creator process's address space, and then the other processes will attach themselves or attach the shared memory to themselves, and then the other processes will also be able to access the shared memory. Okay. All right. Now, if you're going to create shared memory, then of course you have to override the operating system's protections, because now one process is in effect reaching into another process's shared memory, because that's well, one process is reaching into another process's address space, because that's where the shared memory is living. Okay, and but when the shared memory is created and the other processes are attaching to it, the operating system is saying, okay, I'm gonna open up this little hole here for the other processes to be able to reach into another process's address space. But once that has been established, then the operating system no longer has to play a role. Okay. Okay, so how do they exchange data? Well, of course, they just read and write in the shared memory region. Okay. All right. Now, therefore, well, first of all, the shared memory region, all the processes have to be told about it. Okay, so that's one thing. And second of all, these processes have to arrange among themselves, not to step on each other. So you don't want 2 processes, for example, modifying some memory at the same time, because then you have all kinds of problems, as we'll also see later this hour. Okay. All right, so this is very, very convenient, but it does require a lot of cooperation among the processes, and we'll see ways that processes can cooperate. Okay? All right. Often you have producer consumer type of relationship. One process is the producer. It generates the data to put into the shared memory, and then the other process is the consumer. It consumes the data by reading the data from the shared memory. Okay. Now we're going to use a POSIX API to create the shared memory. Okay. Now the shared memory region must have a name. Okay, so when you create the shared memory, you give it a name, and this name has to be known by the other processes. So it could be that everybody agrees on a particular name, and you compile that name into your programs so that, okay, this shared memory region is going to have a certain name, and using that name, then all the processes will be able to access that shared memory. Okay, the shared memory is mapped. Okay, that's the term. Is the shared memory is mapped into each of the other processes so that they can access it. Okay. Quite often, these mechanisms are set up to look like files to the cooperating processes. And so the processes, once all the mapping has been set up, the processes act like they're reading and writing files. And that is another kind of illusion that the operating system can provide. Okay, that means that your programs don't have to do anything really special because your programs already know how to read and write files. Okay, well, let's look at an example here. Okay, okay, here's a program called Producer, and it's the program that's going to produce data for the consumers. Okay, now we have quite often when you make these system calls, you have to include a whole bunch of include files because you have to tell your compiler, okay, what is the signature of these system calls, and they're all defined in these include files. A lot of the system calls require special data types, and of course the data types are all defined in these include files. Okay, so it's not unusual to see, over a half dozen includes. Okay, now the one include that I wrote is globals.h, and you can see here I have a name. Okay, so whoops, looks like I lost a lost a hang on. Dangers of cutting and pasting. It looks like I lost a quote there. Okay, has to be a straight quote. Okay, so so I have a include file, globals.h, and also a buffer size. Okay, now that means that any other process, any other program that wants to access the shared memory will have to know this name. Okay, and so a very common way of doing it is to have a .h file that all the other programs will include that has the common name. Okay? All right, so I've got Compy 142 is the name I picked. Okay, and okay, so we have a file descriptor here. Okay, and we have a pointer to the shared memory object. Okay, and here I am creating the shared memory. Okay, so this is a POSIX call using the name, which is this name here, and then a bunch of flags, okay, and this looks like permissions, okay. So it's going to kind of look like a file, okay. And here I am setting the size, okay. I don't know who comes up with the names for these functions, but it's f_truncate. So I've now created the shared memory and set its size. And now I'm going to map it. Okay, so I'm going to map that shared memory into my address space. Okay, and PTR is just going to be a pointer to the shared memory. Okay, and so from then on, as far as this program is concerned, PTR is just pointing to some memory. And here I am writing a string into it. And what am I writing? It's whatever I passed in as the first argument is what I'm writing into the shared memory. And then I return. Okay, so it's a very, very, very simple application. Okay, now, meanwhile, what's another process doing? Okay, well, here's a consumer. Okay, and again, it includes the same header file and same shared memory file descriptor and same pointer, and it opens that shared memory. Okay, and so like again, the shared memory is sort of kind of looking like a file. Okay? But anyway, so there it goes. It opens it, and after opening it, it can map that shared memory. And so PTR is now pointing at that shared memory, and then it's going to basically write out whatever it found in the shared memory. Okay, so and then it removes, it unlinks. Okay, so here this program, after it's read from the shared memory, it detaches itself. Okay, whereas the here it was basically attaching to that shared memory, and now it's detaching from it. So it's using unlink, which is another file system type of call. Okay, all right. Well, there you go. And well, I should see if the demo works. Okay. Now, as you all know, it's always risky doing demos because demos will always work. Whoops, let me shut this down. This is a Python notebook that's running because I teach a data science class where I do everything in Python. And here in this class, I'm doing everything in either C or C++. And okay, so let's see if I have, okay, shared memory. Okay, shared memory consumer. Okay, so, all right, so what I'm going to do is get the consumer going. Okay, so I'm going to compile the consumer. Okay. All right, so it's, and I should be able to run it. I may have to start the other one first. Okay. All right. Okay, it died because I really needed to start the other program first. So well, I had to start the consumer program first, because it's the consumer program that creates the shared memory. Okay, so let me go there. All right, 142, programs, shared memory producer. Okay, this is where I want to go. And I'm going to open up another folder. Okay. All right, now I'm in the directory where the producer lives. Okay. Okay, so here is the consumer down here, and here's the producer. And I'm going to run this. Oops. /producer. I've already compiled it. And I don't know. I run. Okay, so that's running, and it's written into the shared memory. So hopefully, when I do this, there. Okay, you saw it. It read it from the shared memory. Okay. So okay, not a terribly brilliant program, but at least now you see the mechanism for the producer created the shared memory with a given name, and mapped that shared memory, so that it could just have a pointer to it, wrote Hiron into it, and then here's the consumer program, which then opened that shared memory because it knew the name of it, mapped it into its address space, and PTR was pointing to it, and therefore it could read what was in the shared memory. Okay. When I ran the consumer first, the program died because I didn't put in there any error checking. The shared memory had not been created, and so it just crashed. Okay. All right. Any questions about shared memory? Okay. Now there was no cooperation. Now had both processes been writing into that shared memory, there would have had to have been some cooperation between the two of them so that they don't step on each other. But in this little example, it was the producer that writes and the consumer that reads. And so as long as the producer had already created the shared memory, the consumer can read the shared memory and they won't be stepping on each other. Okay. All right. Well, I'm glad this example worked. Okay. All right. Any questions about shared memory? Okay. So this is one example of interprocess communication. Okay. It is very convenient, very easy to set up, but as you can probably tell, somewhat dangerous because if those processes are not cooperating, all sorts of bad things can happen. Okay. Now in a producer consumer, okay, this is a very, very typical model. You have one or more processes producing data, and you have one or more other processes continuing to retrieve the data, and because all the processes are running at the same time. Okay, so that we'll be seeing a lot of producer consumer types of applications. Okay? And that's where we need to have this interprocess communication. Okay, and then of course I'll keep saying this, in general we need to have those processes synchronized. Okay? And so that we don't have multiple producers writing at the same time to the same place. And if the idea is that anything that's produced is consumed by one consumer, then the consumers may have to kind of take turns consuming. Okay. All right. So chaos can result if they're not synchronized. Okay. Okay. So here's that diagram again. The memory or the message passing model and the shared memory. I just showed you the shared memory. Okay. Okay. Message passing. Okay. Now, if you have small amounts of data, okay, see the shared memory, you can put a whole bunch of stuff in that shared memory, and there's practically no limit to how much you can put in there. It just depends on the size that you create of that shared memory that you create. Now, message passing is really kind of designed for small amounts of data. You're passing messages. Okay. Now here, it's even easier, I guess, to implement than shared memory. You don't have to worry about synchronization because one process is sending messages and the other process is receiving them. So there isn't a chance for processes to step on each other, right? You can have multiple processes sending messages, and they'll go into a queue, and you can have multiple processes receiving messages, and they're pulling them off the queue. you can have multiple queues and so forth. So there isn't that problem with shared memory. Okay. Now, message passing is slower than shared memory because, well, it's done with system calls, and it requires the operating system to actually do something. And so you saw in the earlier lecture what happens when you make a system call that goes down into the kernel. You know, the interrupts and you know, the interrupt handlers and all kinds of mechanisms come into play. And so message passing is not going to be as fast as or as flexible as shared memory, okay? But it's safer, okay? All right, so no shared memory regions. If you have a distributed environment, you know, maybe the processes are running on different machines, okay? If you have the a message passing mechanism set up, each process does not have to know where the other processes are, okay? A process will send messages, they go into a queue managed by the operating system, and there are other processes that are pulling messages off the queue. Those processes, all the processes can be living on different machines on the network, and you know, the person who's sending the message doesn't have to know where the recipients live, and the recipients don't have to know where the sender lives. Okay, so that is a very wonderful concept. Okay. Now, of course, if all the processes are on a network, then we're talking about a network operating system. Okay? But again, the messages are handled by the operating system. Okay. All right. Messages can be fixed or variable length. Now fixed length. It's easier for the operating system to handle them because it knows, okay, they're all the same size. But programming may be harder because, you know, let's say that you set the message length to 100 bytes, and then a message has to be 150. Okay, then therefore it has to be sent as 2 messages, and then the recipients have to put the 2 messages together to make it into 1 message. So there's more programming involved. Okay, variable length. Well, it's easy for the programs because they just get a message, and you know, whatever length the message is the length. Now, operating system then has to deal with variable length messages, so it's harder for the system. Okay, but hey, somebody's already written the kernel code, so if you're a programmer, you probably want to use variable length messages. Okay. Okay, so message passing, you can have cooperating processes refer to each other by name. So if you know the name of the process that you're sending a message to, then just say, hey, this message is going to process X or whatever. Okay, and you know, ahead of time, of course, they've established the link. You know, they you know, figured out, okay, what's your name and how do I get to you and so forth. Okay, and so they work out, you know, how big are the messages? Are we going in one direction only, or are the messages bi-directional? That's all has to be set up ahead of time. Okay. So here we would have, you know, a primitive. Now these are kind of simplified. I'm not going to say that these are POSIX calls, but you know, if you know about the other process P, the recipient, just send a message to the process P, and if you know the sender and you're trying to get a message from that process and you know who it is, then okay, say you're going to receive a message from here, process Q. Okay. Now it may be possible to say, well, I want to receive a message from any process. Okay, so maybe there are a whole bunch of senders, and you're one of the receivers, and you're just going to grab the last message, or you're going to grab the next message that's available. Then you can get the process ID of the sender. Okay? So here, this is direct communication, that the processes know about each other, and they're sending and receiving directly. Okay. Indirect, okay, well, the operating system can maintain mailboxes or ports, and a sender will send a message to a mailbox, and the recipient would get a message from the mailbox, but the sender and receiver are not directly talking to each other. They're going through this intermediary of mailboxes or ports. Okay, so that is another option. Is this indirect communication. Okay, key thing is that we are sending and receiving messages, and so that kind of synchronizes things, right? One process sends, and the other process receives, and so the other process has to wait for a message to arrive. Okay. All right. So when it comes to message passing, we can do it directly or indirectly. Okay. Message passing can be blocking or non-blocking, also known as synchronous or asynchronous. Well, if the receiver of the message, if it blocks, that means that if a message hasn't arrived, then the receiver sits there waiting for the message to arrive, and that, so it's blocked. Okay. And therefore it's synchronized with the sender. It may not know who the sender is, but they're synchronized because the receiver has to wait until the sender sends the message. Okay? Asynchronous means that the receiver checks, is there a message there? And not, then the receiver can go off and do something else, and then later check again. Okay, so there is not is asynchronous because the receiver is not blocked. Okay, it's not forced to wait until a message arrives. Okay, so when you do message passing, you can choose direct or indirect, blocking or non-blocking. Okay. Now, choosing blocking or non-blocking is the choice of the receiver process. So when you write the program, you can say, well, hey, I really need the next message in order to proceed. Then you have to block and wait for the message to arrive. On the other hand, you can say, well, I'll deal with the message when it comes. It's not something that I need to wait for. And so your program can periodically check to see if a message has arrived. But meanwhile, you're doing something else. Okay? Your program's doing something else. Okay? Up to you. Depends on your application. Okay. Okay. So here, blocking send. Okay. It turns out that the sender can be blocked because maybe it's an important message, and you want to make sure that the message is received before you move on. And maybe there's some other communication going on, and the sender really can't proceed until the receiver has actually received the message. And so the sender can block. Okay? And then on the other hand, there could be non-blocking. The sender sends a message and then goes off and does whatever. Okay? Yeah, it could be the case where the sender is sending some important bit of information that's going to affect the way the client operates, and that's going to affect subsequent communications. And so therefore the sender may want to block until it knows that the receiver has gotten the message. Okay. All right. So again, this is a choice that you, the programmer, has to make. Okay. And okay, so we already talked about blocking and non-blocking receives. Okay. Normally, we think of blocking waiting for a message to be received, but as I just showed you, it's possible to block as a sender, block until the receiver has received the message. All right, so here's another example, a socket. Okay, now when we are dealing with networks, okay, we often talk about sockets. Okay, now a socket here is sort of the software uh, view of, you know, hardware. You know what a socket is. You know, it's something you can plug a cable into. That's a socket. Okay, software sockets are kind of like that. Basically, one machine can send a message to the socket of another machine. Now, it's not a physical socket, it is a software socket. You know, so you can sort of think of it as a virtual cable that you're sending a message down. Okay? Because we're talking about networks, you know, sockets are often associated with networking. These sockets will have IP addresses. Okay. IP address to get to the process running on a particular machine, and then a port number. Okay, so that's the particular virtual port that you're talking to. Okay, so the combination of an IP address and a port number is what we're calling a socket. Okay. All right, so sockets. Okay, I actually have a socket example here, even though I don't show it on my slides. It is another really silly example. Okay, let me show that to you. Okay, we did the shared memory. Oh, here's the socket. Okay, so let's take a look at the, first of all, there's a .h file, a header file. And again, I'm going to name the socket. Okay. And then the program, here's the server program. Okay. And okay, it uses the socket name. Okay. Well, first of all, the first thing it does is that it detaches from any previous socket with that name. And so that's the unlink. And then here we create the socket. You can see we have to set up a bunch of parameters, one of which is the socket name. And then we bind to it to connect to our program to that software socket. And then we listen on it. Okay, so this is the server program. Okay? And so here's the server, and it is providing some service. Okay, and so it's going to sit here and wait until somebody connects to it through that socket. Okay, and okay, so let's say that, hey, it accepts a connection from some client, and it's going to read whatever the client sent to that through that socket, and it's going to be a character. And what the server does is that it increments that character. So if it got the letter A, it's going to make it a letter B, and write that character back through that communication channel, and then it's going to close the socket. Okay, so a very, very, very simple server application that establishes a socket, okay, listens for data coming through that socket, which would be just a character, and then it returns the next character, sends the next character down through that socket. Okay, so that's my brilliant server program. And then let's take a look at the client program. Okay, now these are two separate programs. Okay, so here again we will use the same socket name, and socket. Oh, there's client program, and the client program. Okay, creates socket for the client. Okay, names it. Connects the socket to the server's socket, okay? And so there's the connection, okay? It checks to make sure that that connection happened. Okay, it's gonna write the letter A to the socket, okay? And then after doing that, it's gonna read what the server sent back through the socket and write out whatever the server sent back, okay? So as I said, a brilliant pair of programs, but it shows you some of these calls, POSIX calls, to create a socket and to read and write the socket. Okay, so let me see. I think I have that set up already. Yeah, here we go. Socket client. Okay. I've already got this compiled. Well, let me show you compiling. Okay, so this is client.c, and okay, very simple command. I'm just calling the C compiler to compile it. Okay, and I've already compiled the okay. Here, let's compile the server program. There, compile the server program. Okay. Now I'm going to run both of them in the same terminal window. And so I'm going to start up the server program. Okay, so that is there. Okay, it's in a different directory. And I'm going to run the server program in the background. Okay, so it's going to be just running in the background. And okay, and you see it writes out server waiting. And I think you may remember seeing that when the server program starts up, it says, okay, I'm waiting for something to come across on the socket. And now I'm going to start up the client program, which, as you know, writes the letter A. Okay, and okay, so the server read the character A. Okay, so the server program is saying, okay, I read the character A, and it's going to increment the character and write B. Okay, and so I wrote it back to the socket, and the client program, after I wrote the A, okay, that's the client writing A to the socket, well, read back, and the client got the B, okay, and the server's waiting again. Let's see. Okay, it looks like the server is in a loop. Okay, sorry. Server is in a loop, and so I guess we can start this up again. And there we got B back again, and the server is still waiting for us. Okay. All right. So this is client server, okay? And this could be happening across the network. Okay. So what you saw here, the operating system took care of, the IP address and the port number and so forth. Now this is all running on the same machine, and so yeah, there was going to be whatever IP address was default for my laptop. The operating system took care of. Okay. Okay. So any questions about socket communications? Okay. All right, so let me kill the server here. So I'm running it in the background. Server is still running, and remember, we can send programs to the background by appending the ampersand after the name. But if I type FG, it will now say that, okay, now the server program is back running in the foreground, and therefore I can kill it by typing Control-C at it. Okay, so now the server is no longer running. And in fact, see what happens when you try to run the client. Okay, connection refused. Okay, because the server is not running. All right. Any questions about this? Okay, so this is another example of inter-process communication along the models of producer-consumer. Now in this case, the producer, the client and server both played the roles of producer and consumer, okay? But they were synchronized because they were basically sending messages back and forth through the socket, okay? And there wasn't any shared memory, for them to step on each other and so forth. All right, so any questions, okay? Remote program calls, okay? I don't have an example of this, but this is another very powerful feature. If you are on a network and your program is running on one node of the network, and there's another program running on a different node, through remote procedure calls, you can actually call functions of the other program, okay? And that is a truly amazing thing, in that your program is making calls, function calls that are part of another program, and this other program is running somewhere else in the network. That is a truly remarkable illusion created by the network operating system to make it look like you're just making a function call, as if you were just calling a function on your local machine. And it's really going across the network, and the results are coming back across the network. Okay? So that's a remote procedure call. Okay, that's a little hard to set up an example program. Maybe I'll come up with one over the weekend, and if so, I'll send it out. But there is a mechanism that's set up here to make all this work. Okay, so on the client side, okay, the client side is the program that's making the call to the function or procedure in the other program. Okay, so it has a stub. Okay, and this stub is the proxy for the actual procedure that lives on the server somewhere. Okay, so the client program calls this stub. Okay, and what the stub does is that it has the code to find where the remote server is, and it marshals the parameters. What that means is that let's say that this remote procedure takes some parameters. Okay? It's just like any other function or procedure, it has parameters. The stub has to marshal the parameters. In other words, it has to take the parameters that the client is passing and convert them into whatever form is necessary to transmit these argument values over the network. Okay? Maybe it's serializing, maybe it has to do encryption, whatever. Okay? So the stub does that. Okay? Now the client program thinks it's calling the function directly, but it's really calling this proxy, the stub. And then the stub has to find out where that remote procedure actually lives and marshal the parameters, and then send that over the network to the server. Okay. Now the server side has what they call the skeleton. Okay. Now the skeleton then receives the remote call, so it has to unmarshal the parameters. Okay, so it has to put the parameters back into a form that the procedure on the server can handle. Okay, so the server thinks it's just being called by a um, it's just, it thinks it's just getting a regular procedure call, okay? But the skeleton has to make that call after it has unmarshaled the parameters, okay? So the skeleton then makes the call, okay? And so here is a little diagram. So here's the client, okay? Here's the server, the remote object. It makes a call, okay? Call some method. Now the call the client makes is actually to the stub, okay? And so here, what's going across the network are the marshaled parameters, A and B, and then some indication of which procedure or function is to be called. Okay? So this zips across the network to the skeleton, okay, and the skeleton then has to unmarshal the parameters, figure out that, okay, the function that is supposed to be called is some method, and so it makes the call. Now, the some method call doesn't know that this is a remote call. It just seems like a regular call, and it looks like it returns a Boolean value. And so the skeleton has to marshal that Boolean value, and that value comes zipping back across the network to the stub, and then the stub returns the value to the client which made the call, and the client, of course, has no idea that the value, return value, came back across the network. Okay? So this is remote procedure call. Okay. Now, as you can imagine, there a lot of setup has to be done to make all this work, and you know, there often is some sort of configuration file that sort of describes, um, um, you know, gives the signatures of the remote procedures and the data types of the parameters and return values so that the marshaling mechanisms can work. So this all has to be set up ahead of time. And but once it's set up, you know, then programs can make these remote procedure calls. And is you know, I have written programs that have done remote procedure calls, and really you make the call and it's as if you're just calling a regular function, and the fact that it's going across the network is transparent to you. Okay? That's remote procedure call. And okay, any questions about RPC? Okay, you may hear these terms, RPC, okay, remote procedure calls. Okay, okay, you know about pipes already, right? Yeah, you had to do an assignment where you had a process that forked a child process, and then the parent process created a pipe, and you know the parent process wrote to the pipe, and the child process read from the pipe. Okay, so this was all handled very nicely when it was a parent-child relationship, because the child then had the file IDs, because remember when the child was forked, it got a copy of the parent's address space, and in that address space was this uh, two-element array of the file IDs, you know, the file ID of the read end and the file ID at the right end of the pipe, and the child got that information, and so then the parent and child can you both use that pipe. Okay, but what if the processes were created separately? Okay, they're not a parent-child relationship. Well, you can still create a pipe between those two separate programs. Okay. All right. So okay, I'm just describing the parent-child relationship, and you're already familiar with that, right? You know, this is that two array of two file IDs, and there's the pipe, and there's the parent. It writes to the right end of the pipe using the right file ID, and there's the read end, but then the parent is not going to use that. There's the child, and it knows the write end of the pipe, and it also knows the read end of the pipe. Okay, and as you saw, the parent doesn't use the read end, and the child doesn't use the write end, and so this is what you did for your assignment. Okay, and I showed you examples of this in class. Okay. All right. Well, this is fine and good if you have a parent-child relationship, okay? And both parent and child know about this file descriptor array. Okay? All right. Well, how about two independent processes? Okay, they were started up totally separately. I probably shouldn't use the word independent. Maybe I should say two separate processes. Okay, let me change that, because I had said independent earlier means that they didn't have to cooperate. I really have to be careful of how I use words here, because they have specific meaning. Do separate. Okay, how's that? Okay, so these are two programs that you start up, okay? And they're not in a parent-child relationship. Okay, so you create a named pipe, okay? And it's basically just like with the shared memory and with the sockets, these processes agree on a name, okay? And you create a pipe, give it a name, and therefore the processes can access this pipe, okay? Now, a named pipe is also known as a first in, first out queue, a FIFO queue, okay? And the thing about FIFO queue is that it's bidirectional, right? Just like that socket connection that you can read to it and you can write. You can write to it and you can read from it. Okay, so there's a POSIX call, make FIFO. Okay, and interesting thing about is that once you've created this named pipe or this FIFO queue, it stays around until you reboot the machine or until somebody specifically goes in there and destroys it. Okay, so it's persistent. Okay, once the FIFO has been created, any process can open it for reading or writing. Okay, and in fact, both ends of the pipe need to be opened simultaneously in order for you to do this reading and writing, of course, right? Then that makes sense. So as long as a process knows the name of this FIFO queue, then it can open it, okay? And again, these things are made to sort of kind of look like files so that your program can act as if it's reading and writing files. Okay. All right, so I'm going to do another silly example. I'm going to create two processes, okay, and they're going to have a named pipe or FIFO that they can work between them, and it will have this name, okay, which is supposed to look like a file path, okay. And this is the file path I've chosen. Okay, and the first process is called write read because at first it reads. First it writes to the pipe and then it reads from the pipe. Okay, so it's constantly doing write read write read write read. Okay, the other process first reads from the pipe and then writes to it. So it's doing read, write, read, write, read, write. Okay? So of course, then if we have these two together, then they're basically exchanging messages back and forth. Okay, so they are cooperating in a way, but in a very kind of elementary way. Okay, so here is write read. Okay, this is the process that first writes to the pipe and then reads. Okay, so here's globals.h, which has the name of path name of the FIFO and some buffer size. Okay, so we create a message of that buffer size. Okay, here I'm making the FIFO with the path and the read-write permissions. Okay, so this guy is now going to be in a loop, and it opens the FIFO. Okay, now it reads a message from standard in, and so I'm going to type something on the keyboard, and then what it does with that message that it read from the keyboard is it writes that message to the pipe. Remember, FD was opening of that our pipe. Okay, all right, and then it closes it. Okay, then it reopens the pipe for reading. Okay, and then it reads from the pipe. Okay, and whatever it read from the pipe, it writes it out to a standard out. It does a printf, and then it closes the pipe. Okay, and then it loops again, reopens the pipe for writing, gets a message from the keyboard, and writes it to the pipe. Okay, so it's doing a write, read, write, read, write, read. Okay, where what is writing is whatever it read from the keyboard. Okay? Now the other process, the read write, okay, has the same globals. Okay, here it is, creating the name pipe. Make FIFO, of course, is basically saying is creating the logical connection to that FIFO, and here it is opening it for reading. Okay, it reads the pipe, and then whatever it read, it writes out to the terminal, closes the pipe, reopens it for writing, gets a message from the keyboard, and then writes whatever message it got to the pipe and closes it again. And then it's in this read, write, read, write, read, write loop. Okay. So, okay. Let's see if we can get that working. Okay, let's see what I have here. Name pipe. Okay. This is the write read. Okay, there it is. I've already compiled it. So, and then here is the read write. Okay, I have already compiled it. Good. So let me run both of these. Okay. Okay. So let me get this one going. This is the read write process. So it's going to hang or block waiting for something that comes from the pipe, and this is the write read. Okay, and I'm going to say now it's waiting for me to type something so I can write that to the pipe. So I can say hi. Okay, now when I hit carriage return, it's going to write that to the pipe, which then is going to be read down by this process. So keep an eye on both of them. See, it got high class from the other guy. So from the write read process, which is this guy, it got high class. And okay, now it's waiting for me to type something. I don't know. Which then when I hit carriage return, this guy will get. Okay, so there it is. What's going on? All right, so we can bounce back and forth. This guy got it, and say by here. Whoops, by here too, and that guy got it. And if the way I've written the program, if it gets a zero length message from the terminal, it's going to shut down this guy, and that's going to cause this guy to shut down too, because I write the zero length message to the pipe, and when it receives a zero length message, it's going to shut down. So here, I'm just going to hit carriage return. And so now you can see both of them finished. Okay. All right. That is a named pipe. And as you can see, it can be very useful. Okay. It's that program that you wrote for the assignment, where you had to read that CSV file and then generate the HTML page. The two programs which you wrote separately and then use the pipe operator to connect the two of them on the command line, you could have written them as two completely separate programs, but then connected with a named pipe, and you could have done the piping without having the shell do it. Okay, so you can see there are multiple ways that you can do things, and as you learn more about the capabilities of the operating system, POSIX calls, and what bash shell can do for you, boy, you're adding more and more tools to your toolbox, and you'll be able to be a much more effective software developer. Okay. All right, so that is a big goal of this class is to give you those skills so that you can blow away the interviewers when you go out for looking for jobs. Okay. All right, this is a good time to take a break because I've shown you a lot of mechanisms where multiple processes can communicate. And after the break, I'll talk about, okay, well, how can we get these multiple processes to cooperate, to synchronize so that they don't step on each other. Okay, so we'll take a break. How about breaking until okay? It's almost 1:15. How about breaking until 1:25? Okay, and as I said, I don't want to run over this class because I got to dash over to the fairgrounds and get my first COVID vaccination shot. Okay, so break until 1:25. I'm going to stop sharing and pause the recording and go mute. And at 1:25, we'll come back. Okay, but before I pause, any questions? Okay, I know I'm hitting you with a lot of system calls and example programs, but first of all, nobody memorizes these things unless this is something you do all the time. So I just want to let you know that these capabilities are there. And here are the calls to make it happen. And I'm only showing you simple examples. You can go online and read all about all the various parameters you can pass and all the different things you can do. But at least now you know that functionality exists. Okay. All right. If there are no questions, then I will go ahead and pause for the next 10 minutes. Okay. Okay, we're back. Okay, let me share my screen. All right. Okay, so you saw the various ways that processes can communicate with each other. Now let's see how they can synchronize with each other so that they don't step on each other while they're trying to communicate. Okay, so multiple cooperating processes executing concurrently, of course, must synchronize so they can share information, do message passing. You don't want them stepping on each other. Okay. Now, one way to cooperate is to make sure that the processes synchronize or sequence their operations. Okay, so this is where one process depends on another. For example, process B is depending on some output generated by process A. Okay, so this was the client producer consumer model that we saw, because that's one way of sequencing is that B has to wait until A produces the output, okay? Now, when you have, say, shared memory, okay, where it's, you're not using a pipe or a socket, shared memory, as you saw earlier, is extremely flexible, extremely powerful, but you got to be really careful how you do it. Otherwise, you may have what's known as a race condition. Okay, when multiple processes are accessing and modifying shared data, and the final result of whatever operations that they're doing, if the final result depends on the order of execution or the order that the processes modified the data, okay, then you have a race condition, okay, where the final result depends on order, okay, the order the processes modified the data. This is a very, very bad situation because the results are unpredictable and unrepeatable and extremely hard to debug, okay, because when you have multiple processes and the operating system is controlling, running them, you have no control of the order that things can occur unless you put in synchronization mechanisms, okay? So race condition is a very bad situation, okay? Impossible to debug because, you know, something bad happens and then you run it again and it doesn't happen. And then you run it under debugger while the debugger affects the timing of things, and yeah, it's very, very bad situation, okay? So let's take a look at an example of a race condition, okay? Let's say that you have two processes and they're both accessing a variable, let's call it count, that's in shared memory, okay? And let's say that you want to do count plus plus, okay? And so how would that get compiled, okay? Well, the code would say move count to a register, register 1, increment register 1 by 1, and then assign the contents of register 1 back into count. So this is one way that count plus plus could be implemented, okay? Count minus minus, okay? Let's say the other process is doing count minus minus, and it puts count into register 2, decrements register 2, and then assigns the contents of register 2 back into count. So that's how count minus minus could be implemented, okay? And now these are two separate processes, or they're two separate sets of registers and so forth, okay? All right, now let's suppose that count has the value 5. And process P1 does the count plus plus, which I have in green, and process P2 does the count minus minus, which I have in red, okay? So here, count starts out at 5, and on the left-hand side is what P1 is doing, and on the right-hand side is what P2 is doing, okay? Now, let's see what can happen if the two processes are not synchronized and they're both accessing and modifying count at the same time, okay? All right, well, here's sort of a timeline of what's happening. So P1 moves count into register 1, so we're gonna follow the green code here. And so register 1 now contains the value 5. P1 increments register 1, and so now register 1 contains 6, okay? Meanwhile, P2 moves count into register 2. Well, count hasn't changed, and so now register 2 has 5. This is register 2 of this other process, and count our process P2 decrements register 2, so now register 2 has 4. Okay, all right. Now over here, P1 now assigns register 1's contents to count, and so if P1 runs here, count becomes 6. Okay, and meanwhile, process P2 does the same operation, and now count has 4. Okay. So, well, what if these last two operations happen in the other order? Okay. Then, well, the way I have it now, count's going to end up with the value 4. Okay. Had these last two operations happened in the other order, like the red happened for the green, then count would have ended up being 6. Okay, so this is a race condition where the final value, the final result depends on the order of execution. Okay, and you can imagine how hard this would be to debug. You know, the person writing the green code expects count to be 6, and all of a sudden sees that count's 4, and vice versa. The person writing the red code expects the count to be 4, and depending on the order of execution, could have gotten 6. Okay, and so you try to debug this, and you know, as I said, you have no control over the timing because it's the operating system that is running these two processes, and you know, machine interrupts, I/O operations, paging in and out of you know, virtual memory, all kinds of things will affect the timing of the running of these two processes, and so we have a race condition, and this will be impossible to debug. What you learn is that if you debug a program where timing is important, the fact that the debugger is in there is affecting the timing. Obviously, if you put a breakpoint and the program hits the breakpoint, that affects timing, and so you don't want race condition. Okay. All right, let's see how we can avoid race condition. Okay. Now, there is a concept called mutual exclusion. Okay, one way to avoid race condition is to prevent more than one process from reading and writing the shared data at the same time. See, the problem here is that P1 and P2 were both reading and writing count at the same time. Okay, so you want to prevent that. Well, one way to avoid a race condition is to prevent the situation where more than one process is reading and writing the shared data at the same time. This is called mutual exclusion because they mutually exclude each other. One process is writing to a bit of shared memory. The other processes are excluded from writing to that same shared memory. So that's the idea behind mutual exclusion. And mutual exclusion is something that you ask the operating system to enforce, right? One program by itself is going to have a hard time keeping out other programs from accessing shared memory. And so you ask the operating system, hey, can we agree on mutual exclusion so that when my program is accessing the shared memory, the other programs are blocked from doing the same thing? Okay, so if we have mutual exclusion, or if we have any sort of shared data, then you have the concept of the critical region, also known as critical section. Okay, it's the part of a process's code that operates on some shared data. Okay, and it's easy to confuse what a critical region is. Critical region is code, not data. The data is the shared data. Critical region is that code within a process that accesses the shared data. Okay, so if you have some shared data and you have, say, two processes that are accessing that shared data, therefore the two processes have a critical region, each has a critical region with respect to that shared data, you want to prevent two processes from being in their critical regions at the same time for some shared data. Okay? So that is mutual exclusion. Okay, if your process is in a critical region, you want to prevent other processes from being in their critical regions. Okay, because the critical regions are where you access the shared data. Okay. Okay. That's what mutual exclusion is all about. Okay. Now, how are we preventing race conditions? Okay. Mutual exclusion. That's going to keep more than one process from trying to read and write some shared data at the same time. Okay. Progress. Okay. If a process is running outside of its critical region. So I have a process and my process is not in the critical region. I'm not allowed to block other processes. Okay, I'm only allowed to block other processes if I'm in my critical region. Okay, bounded waiting. Okay, if a process is blocked, okay, meaning that it cannot enter its critical region because another process is already in there, in its critical region. The waiting time has to be bounded. I mean, you can't wait forever. Okay, so, all right. So we got to make sure that a process isn't blocked forever, waiting to enter its critical region. Okay. When a process is in its critical region, okay, meaning that it's accessing the shared memory, other processes have to be blocked. Okay, so if there are other processes that have critical regions where they're accessing the same shared memory, if my process is already in my critical region, I gotta block the other processes. Okay. Now, all this talk about blocking and waiting, et cetera, have nothing to do with the number of CPUs that you might have in your system or their speeds or whatever. Okay, so whether these processes are running on different CPUs or they're running on the same CPU, we talked about this in earlier weeks, how we can do process or task switching if you have only one CPU, or the processes can be running on different CPUs. This whole mechanism that I just described is independent of the CPUs. Okay? So all we care about are multiple processes, each with a critical region accessing the same shared region, shared memory. Okay? Okay, so here is a little diagram, a timeline. Okay, so here's process A. It's charging along. Oh, time moves from left to right. Okay, so here's process A, and it enters its critical region because they're between A and B. There's some shared memory, and now A wants to do something with that shared memory, so it's in its critical region. Okay, now meanwhile, here's process B. Okay. So A entered its critical region at time T1. So now it's executing code that accesses the shared memory. Now B is charging along, and at T2, it wants to enter its critical region where it's going to access the same shared memory, but it's blocked because why? Well, it's because A is in its critical region. So it has to wait until time T3 when A is done, leaves this critical region, and now B can go into its critical region, and it eventually leaves the critical region. Okay, so A and B both have a critical region. That's the code that accesses the shared memory. Okay. All right, again, do not confuse critical region with shared data. Maybe I'm the only one who, when I get careless, I maybe confuse them in what I say, but I suspect other people do too. Critical region is code, not the data, okay? Now the code in the process, okay, that accesses the shared data, of course, is that process's critical region with respect to that shared data. And if we have multiple processes that access the same shared data, their critical regions could be different. For example, one process's critical region can be writing to that shared data, and the critical region of the other process can be reading from that shared data. So the critical region is not shared code, okay? It's the data that's shared. The critical region is critical because it's accessing that shared data, okay? So that therefore every piece of shared data has a corresponding set of critical regions among the various processes that access that shared data. If there's another piece of shared data, then there'll be another set of critical regions where the processes are accessing this other piece of shared data. Okay, so let's just concentrate on one piece of shared data and one set of critical regions among various processes. Okay, so now we know what a critical region is. Okay? So how do we then enforce mutual exclusion so that when one process is in a critical region, the other processes are kept from going into their critical region. So they get blocked and have to wait. Okay, so this is all done with locks. Okay, and let's say there's a shared lock variable. Okay, so maybe the lock variable is itself shared, and the value of the lock variable is either 0 or 1, to indicate whether it's locked or unlocked. Okay, so if a process wants to enter its critical region, it checks that lock. Okay, and if the lock is 0, okay, meaning that it was unlocked, then it sets the lock to 1, so locks that lock and enters the critical region. Now, if the lock is already 1, that set to 1, that means somebody else is in its critical region, and the process has to sit there and wait until the lock becomes a 0. Okay. I should probably have written here that it enters this critical region, and when it's done, it sets the lock to 0 again. Okay, so okay, let me add that there because okay, when it finishes the critical region, oh, how about when it leaves the critical region? It sets the lock to 1. 0. How's that? Okay. It's important because you can imagine if a process sets the lock to 1 and goes into its critical region and leaves and forgets to set the lock back to 0, that means that all the other processes that were blocked waiting to get into the critical region will never go in because that lock is always locked. Okay. All right. So that's very important. I should not have left that off. Okay. All right. Okay. So there we go. Okay. All right. So lock value 0 means there's no process currently in this critical region. Lock value 1 means that somebody is in its critical region. Okay. Now, what's the problem with this solution? Okay. Here, we're going to treat the variable, the lock, as just a variable. And obviously, that variable has to be shared. Otherwise, well, it has to be shared so that all the processes that have a critical region will know to check that lock. Okay. Any ideas? What's wrong with this solution? Is anybody out there? Now remember what we talked about before the break. if the lock variable is itself shared, well, who protects? Then does the lock variable itself need a critical set of critical regions, right? If we treat the lock variable as just another shared variable, we can have a race condition testing and setting the lock. Okay, just as I showed you earlier with the count plus plus and count minus minus. Well, we can have a race condition, and then so the shared lock variable isn't going to work because of the race condition. Okay, so the very thing that we wanted that lock variable to protect against, it itself is subject to a race condition. Okay? All right, so lock variable is not going to work. Okay, well, how about this thing called busy waiting? Okay, well, we have a shared turn variable. Okay, all right, so I think now whenever I use the word shared, alarm bells should go off. But let's move on. Okay, so when turn, okay, we're assuming there are two processes, P0 on the left and P1 on the right. Okay, and turn tells whose turn it is to go into its critical region. Okay, so here, down here, I've got a function called critical region. Okay, so whatever that function is doing is accessing some shared memory. So it's the critical region. Okay. All right. So now here's P0, and if turn is not equal to P0, that means it's not P0's turn. So it will just sit here and go round and round and round, waiting for turn to become 1. Okay, and then finally, when turn is no longer 0, presumably now it's turn equals 1, it can go into its critical region. Okay, and then when it's done with the critical region, it can say, okay, now it's the other guy's turn. Okay, so it sets turn to 1, and then it can do non-critical stuff. Okay, and then here's P1 is doing the same thing. It's waiting for its turn. So as long as turn is not equal to 1, it's going to sit here in this tight loop doing nothing. Finally, turn becomes 0 because maybe, well, because P0 finished its critical region. So it set turn to 1. And so now the while loop can end. P1 can do its critical region. And then it can say, well, okay, now I'm done with my critical region. It's the other guy's turn to do whatever. And then it can do its non-critical region stuff. Okay, so this is busy waiting, and it's called busy waiting because the way we do the wait is just to have the process sit there spinning, doing nothing. So it's stuck in this while loop, doing nothing, waiting for turn to change its value. Okay. All right. Well, I'm sure people can see issues with this. Now, turn is shared. Okay, but we can kind of guess that maybe setting the value of turn to a value, to 1 or a 0, checking the value of turn. If we assume that that's done with one instruction on the machine, then we can say, well, it's not as bad as when we were implementing count, where that requires several instructions, and therefore the other process can jump in, in the middle of our sequence of instructions. Okay, so let's not worry about the fact that turn could be subject to a race condition. Okay, but let's just concentrate on what we're trying to accomplish here. Okay, so we're doing this busy waiting. Okay, any comments about busy waiting? Okay. what's happening to the poor CPU that P0 is running on, and while it's busy waiting? Okay, that CPU is kind of tied up. It's just going to sit there and yeah, I'm sure the CPU is going to hit 100%. Well, when it's in this tight loop. Okay, and then same thing with the CPU that P1 is running on. And that's assuming they're running on two different CPUs. I mean, if they're both running on the same CPU, when one of them is in this tight loop, can the other process even get a chance to run? You know, well, maybe if we're doing round robin time slicing, okay, but you can see that busy waiting is kind of wasteful. Okay, all right, so. And then this depends, of course, on the fact that they are taking turns going into critical regions. I mean, here, let's say P0 finishes its critical region and sets turn to 1. And let's say that P1 never sets turn back to 0, then we're going to be spinning here forever. So there are problems with this solution. Okay, so okay, yeah, what can go wrong with taking turns? One of them doesn't take a turn, the other one is stuck in its while loop. Okay, so the definition of busy waiting is you're continuously testing a variable until it has some value. So here, where we're continuously, maybe the term should be continually, but anyway, you're over and over and over again testing turn to see if it has some value. Okay, and this is called a spin lock because, well, guess what? So this while loop is in effect a lock, and you're spinning. You're going round and round and round, constantly checking turn. Okay, waste CPU, and boy, you don't want to do this if the wait is a long time. And it's a poor choice if one process is slower than the other. So maybe process 1 is doing some really fast calculations, and process 2, its critical region is taking a long time. Maybe it's doing I/O. Who knows? Okay, so this slow process is keeping the fast process, spinning for a long time. Okay, so not busy waiting is probably not the best way to implement a lock. Okay. All right. Any questions about busy waiting? Okay. Okay. Well, I forget who Peterson was, but he came up with this solution. Okay. All right. So again, we have P0 and P1, and they share a variable turn and a Boolean array called flag. Okay, and this array has as many elements as there are processes. Okay, so all right, well let's see what's happening here. Okay, here's P0. Okay, it says it sets flags up 0 to true. Okay, and it says that, well, right now the other guy's it's the other person's turn, so it sets turn to 1. Okay, all right, well here's the busy wait. Okay, while flag sub 1 is true, okay, and turn is equal to 1, okay, it's going to busy wait. Okay, and when either of these two becomes false, okay, then it can go into its critical region and it sets flags of 0 to false. Okay, and if you look at the other guy, well, it's sort of the flip of P0. Okay, it says flag sub 1 to true. It says turn to 0, saying that, hey, it's the other guy's turn to do its thing. And here's the busy wait. Okay, as long as flag sub 0 is true and turns equal to 0, then it's going to be busy wait. But as soon as either of these two conditions becomes false, then P1 can go into its critical region, and when it's done, it sets flag sub 1 to false. Okay? Well, I think we can tell what the purpose of turn is. It basically says whose turn it is to go into its critical region. But then what is this flag array? Okay, it's a Boolean array. Let's see. Okay, so here it is again. Okay. First of all, if we look at this, you know, ignoring possible race conditions of turn and the flag array, which obviously turn and flag are going to be shared between these two processes. So let's ignore for now possible race conditions of those two. Okay. Now, first of all, this will make sure that P0 and P1 can never be in their critical regions at the same time. Okay, and how does it work? Okay, if P0 is in this critical region, that means P0 is in this red function. That means that P1 is false. Okay, that means that P1 had just left its critical region. See, because this is what P1 does. Turn is 0. Okay, that means it is P1's turn to go in. So either of these conditions is true. So if either turn is 0 or P sub 1 is false, then that means that we break out of this busy wait and P0 can be executing. Okay. Now, what does it mean that P sub 1 is false? Well, it means that P sub 1 wants to go into its critical region. So here, P0 is announcing that, hey, I want to go into my critical region. Oh, but it's the other guy's turn. And here, P sub 1 is saying that, hey, I want to go into my critical region, but it's the other guy's turn. Okay, so that's how they end up doing busy wait. Okay, now if turn is 0, that means that P sub 1 is now trying to enter its critical region, but it's waiting for its turn. Okay, so turn being 0 says that the other guy cannot go in. P sub 1 is waiting to enter its critical region, and it can't go in. Okay? So in both cases, either of these two is true. That means that P sub 1 cannot be in its critical region when P sub 0 is in its critical region, and vice versa. Okay, so this was a solution that this person Peterson came up with. Okay, and still it involves a busy wait. Okay, you can sort of study this and see how this can be an improvement over just this, where we just have the turn variable. And here, what Peterson added was this flag array, okay, that says, hey, I want to go in. I want to go in. And I think if you look carefully, what it does is that it avoids the problem where here we were relying on the fact that they were alternating going into the critical region, and then when one of them decides not to go into the critical region, the other person ends up stuck busy waiting. Okay, and so Peterson made it so that we weren't relying on the fact that they had to alternate going into their critical regions. Okay, all right. Well, that was Peterson. Okay. Here's yet another solution. Okay, This is the test and set lock, okay? Now, there are machine architectures that have a single machine instruction that does what I show here, okay? And therefore, that single instruction cannot be interrupted. So that instruction has to do all these operations and never be interrupted. So basically we're guaranteeing that once this instruction starts executing, it will go all the way to the end. In other words, that this function will go all the way through without being interrupted. Okay, so here's test and set lock, and it does something kind of bizarre. You pass in by reference a Boolean target. Okay, and I know that okay, so it's either true or false. Okay, and we're passing that in by reference. Okay, so we store away the original value, the value that was passed in. Okay, then we change the value to true. Okay, and it was passed by reference, so that means the actual argument was changed, set to true. But then what the function returns is the original value. Okay, so whatever was passed in is what the function returns, but as a side effect, it set the target to true. Okay, and again, this cannot be interrupted. Okay, so let's see how this would work. Okay, all right, so we okay, I just explained all this. Okay, all right, now if the original value was true, okay, that means when it was passed in to begin with, what was true, then this function would return true, okay? And a process is not allowed to enter its critical region in that case, okay? So that means the lock was set, okay? Remember, test and set lock always returns the value it was passed in, but then it changes the target to true, okay? So if the original value, if target was already true, then test and set lock will return true, okay? All right, so here we go. There's our function again, and here is here is the test and set lock being used. Now, eventually, okay, so as long as lock is true, right? Test and set lock will return true, and we're stuck in this loop. Okay, true meaning the lock is set. Okay, now presumably some other process, when it finishes its critical region, is going to set the lock to false. Okay, which means that this process will now return false, because some other process set the lock to false, and test and set lock always returns the value that was passed in. And so now we break out of this loop, okay, and we can go into the critical region. But remember, test and set lock also set the lock to true. So while we're executing in here, the lock is set. Okay, and then when we're done, we set the lock to false. Okay. All right, so this solution, okay, relies on there being this atomic instruction called test and set lock. It's a machine instruction that does these operations in a non-interruptible mode. Okay, and this is yet another mechanism. Now this one requires hardware support. It requires that there be this machine instruction that is non-interruptible. Okay. All right, and well, that's why TSL has to be atomic. Otherwise, if it's not atomic, then well, we could have a race condition. that another process can be executing test and set lock, and its execution can get interspersed with our execution, and we have a race condition, and test and set lock will then become useless. Okay, so that's why TSL has to be atomic. Okay, and as I said, there are machines that have such an instruction, and it's used for this kind of purpose, to enforce mutual exclusion. Okay. All right. Any questions about this guy? Okay. All right. So all the solutions I've shown you up until now involve busy waiting. Okay. CPU is sitting there spinning away inside this while loop, tying up CPU cycles and wasting them. Okay. And so busy waiting is not the best thing. Okay. Priority inversion problem. Okay. Here's a problem that can occur with busy waiting. Okay. Let's say that we are doing preemptive process scheduling. Okay. And in fact, we're using high priority first type of scheduling. Okay. So high priority H. It always gets to run whenever that process is ready, because it's high priority. The operating system suspends whatever is currently running, and H gets to run. Okay, so it's preemptive, high priority scheduling. Okay, and there's some poor, low priority process. Okay, and let's say that H and L share some data, and so both of them have a critical region. Okay, and let's say L is inside this critical region and is doing something that it, accessing some resource that it shares with H. Okay, H then is going to go into a busy wait loop because L is already in the critical region. Now, but H, remember, is high priority, and so it's running, and so it's running inside its busy loop. L never gets a chance to run again because it's a lower priority, and so it never gets a chance to leave its critical region. Okay, so here the situation is that L is suspended inside of its critical region because H had higher priority, and H is in its busy loop, waiting to go into its critical region, but it can't because L is in its critical region. And well, you can see that H and L have both ground to a halt. Okay, and so both processes hang, and H is forever busy waiting. Okay, so this is an example of some of the dangers that can occur if you have busy waiting and you are, in this case, we're doing a high priority type scheduling, and it's preemptive, which means that H, or when H started running, L got preempted, and even though it was in the middle of its critical region. And then when H went into a busy loop, waiting to go into its critical region, everything grinds to a halt. Okay, so this is not good, obviously. Okay. All right. Well, here's another mechanism. This is again the producer-consumer model, and we're using sleep and wake up. Okay. So we're assuming that producer and consumer are two processes that are sharing a buffer of some sort, and producer is producing items to put into the buffer, and consumer is pulling items out of the buffer to consume them. Okay, so here producer is in a loop producing items to put into the buffer, and the consumer is in a loop consuming items. Okay. Now, so here, let's see what producer is doing. Okay, it produces an item. Okay. Now let's assume that the buffer has size n. Okay, and so if the count of the items inside the buffer is n, that means the buffer is full. Okay, and so it cannot insert the new item that it just produced, so it goes to sleep. Okay, so it's asleep. The process is suspended. Okay, now if it wakes up, and we'll see how it wakes up later. If it wakes up, then presumably the buffer is no longer full, and so it can go ahead and insert the item. Okay, and then of course it has to increment the count to say, well, you know, how many items there are in the buffer. Now, if the count becomes 1, you know, after we increment it, that means the count was 0, which means until we inserted this item, the buffer was empty. Okay. Now that we have inserted the item, and there's at least one item in the buffer, we can wake up the consumer. Okay. Well, why was the consumer asleep? Well, let's take a look at what the consumer is doing. Okay. The consumer says, well, hey, if the count is 0, that means the buffer is empty, and therefore it goes to sleep. Okay. And so this is the wake up, to wake up the consumer from sleeping. Okay. Now, when the consumer wakes up, presumably there's at least one item in the buffer, and so it removes the item and decrements the count. Okay. Now if the count after decrementing is equal to n minus 1, that means it was n, which means the buffer was full. Okay, but now it's no longer full because we just took an item out of it, and so we wake up the producer. And remember, the producer was sleeping if the buffer was full. Okay, and then of course the consumer can consume the item that it just took out of the buffer. Okay, so this is a very typical producer consumer. Yeah, and we got a producer process, we have a consumer process, and they sleep and wake. They sleep when they have to, and they wake up the other when it's appropriate. Okay, so okay, any questions about what's going on here? Okay, so this is the sleep and wake up method. Okay, for the producer consumer. Okay, all right. So well, again, we could have race conditions. There's count plus plus, count minus minus. Okay, and I showed you earlier what can happen. Okay, so let's see what bad thing can happen. Okay, so here, let's say the buffer is currently empty. Okay, and so the consumer, okay, when it runs, oh, count is equal to 0. Wonderful. Okay, but right at that moment, the producer runs, and it increments count to 1, okay, because it inserted an item, and then it says, oh, I got to wake up the consumer because now the count has become 1. Okay, but remember, back over on the consumer side, it just checked to see that count was 0, but it hadn't yet gone to sleep. Okay, so this wake-up call was kind of wasted because the consumer hadn't gone to sleep yet. Okay, all the consumer had done was verify that count is equal to 0. Okay, all right. So the wake-up call is lost. Okay, but now the consumer goes to sleep because it saw that the count was 0, right? And now the producer then fills up the buffer, okay, and then it goes to sleep, okay, and the consumer is asleep, and so now both processes are sleeping, okay, and so that was because of the race condition that occurred, okay, with the variable count, okay. consumer saw that count was 0, but before it could go to sleep, the producer incremented that count and then tried to wake up the consumer. Okay, but the consumer was not asleep at that point, but then it does go to sleep. And then meanwhile, the producer fills up the buffer and goes to sleep. And so now both the producer and the consumer are sleeping. Okay, this is called a deadlock. Deadlock is when everything freezes and yeah. Okay, so sleep and wake up is, it looks like a good idea, but we had a wasted wake-up call here, and then after the wake-up call, consumer went to sleep, and by then we were doomed. Okay, so the operating system then, finally, what is the operating system going to provide to help us do process synchronization? Semaphore. A semaphore is a way to keep track of the wake-up calls so we don't lose them. See here, we called wake up and we lost it because consumer wasn't asleep yet, and then that wake-up call was lost. Okay. All right, so semaphores are a mechanism to keep track of things like wake-up calls. Okay, so a semaphore is a shared variable. It holds an integer value and it has atomic actions. Okay, so if S is a semaphore, you can wait on S. Okay, and what's happening when you call wait is that as long as the semaphore is less than or equal to 0, we block. Okay, and then when we unblock, we decrement S. Okay, so wait is like we're keeping track of the wake-up calls. Okay, and then signal is basically we just increment S. Okay, so there's that, but that's what signal does. Okay, now this is not quite as bad as a busy wait because we actually do block. Okay, and we block until S becomes a positive. Okay, and then we unblock and decrement S. Okay, well, let's see how and again, these are atomic actions. Okay, so either with hardware support or certainly the operating system is going to make sure that wait and signal are atomic operations. Okay. All right. So this is known as a counting semaphore because we're counting here. S is keeping track of a count of something. So it's called a counting semaphore, but usually we just call it a semaphore. Okay. So we use a semaphore to ensure that processes that depend on each other will execute in the proper sequence. So for example, we have two statements here, S1 and S2, and by doing the waiting and signaling, we are guaranteeing that S2 will execute after S1, right? Because this process is waiting on this semaphore, okay? And so S1 will run. So S1 is executing first, and then it signals the semaphore, which then allows S2 then to run. Okay? So semaphores have to do with synchronization. So these two guys are synchronized. We're guaranteeing that the order of execution is S1 and then S2. Okay. All right. Now, there's something called a binary semaphore that has only the values 0 and 1. So you see the counting semaphore, S can have values other than just 0 and 1. Okay, there's a special binary semaphore that has only the values 0 and 1, and that's called a mutex. Okay, mutex stands for mutual exclusion. Okay, so here's how we would use a mutex. Okay, you have a critical region here. Okay, and you wait on the mutex. Okay, and when the mutex allows you to go in, you do the critical region, and when you're done, you signal on the mutex to allow another process that may have been waiting on the mutex to then proceed. Okay? So a mutex is enforcing mutual exclusion. You can only have one process in this critical region. Okay, whereas a semaphore is used for synchronizing. So an easy way to remember this is that S, semaphore starts with S, and synchronizing starts with S, and mutex is short for mutual exclusion. Okay. All right, so if we have semaphores and mutexes, then we have a chance of enforcing mutual exclusion and making sure that processes are synchronized without busy waiting and without, without busy waiting. Okay. All right, so now let's take a look at our producer and consumer problem. Okay. Now, we have to make sure that they operate in proper sequence, right? Because the producer cannot enter an item into a full buffer until the consumer consumes an item, and the consumer cannot retrieve an item from an empty buffer until the producer produces an item. And so there's synchronization involved there, okay? And obviously the buffer itself is shared, and so we will need mutual exclusion. Okay, so we need both synchronization and mutual exclusion when we have producers and consumers. Okay, so I'm going to say we have a semaphore called empty slots available. Okay, it keeps track of a number of empty slots in the shared buffer. Okay, and so we initialize it to the buffer size because initially the entire, all the slots are available, okay? And we have a semaphore called filled slots available, and that keeps track of how many slots are filled, and we initialize that to 0. Okay, so these are semaphores, okay? Before we add an item to the buffer, then we have to wait on the empty slots available semaphore. You have to wait until there's an available empty slot because the buffer could be full, okay? Now, if the count is equal to the buffer size, you know, the buffer is full, and so this is a way to get the producer to block, okay, because it's waiting on the semaphore, okay? And then if the an empty slot does become available, then of course the producer can enter something into that buffer and decrease the count of empty slots, okay? And after adding an item, okay, it's going to signal the filled slots available semaphore because that's what the consumer was waiting on, and it will increase the count of filled slots by doing that signaling, okay? All right, so, and then before removing an item, now this is on the consumer side, it waits on the filled slots available semaphore, because if the count was 0, I don't see how it can ever become negative, but if the count was 0 or negative, the buffer was empty, So therefore, the consumer had to block, and that's why it was waiting on the filled slots available. And then when it does that wait, when it's done with the wait, it decreases the count of filled slots, okay, because it's going to take away an item from the buffer. Okay. Now, after removing an item, it's going to signal the empty slots available, okay, saying that, okay, now there's another empty slot available, which then, of course, increases the count of empty slots, okay, because that semaphore was keeping track of the number of empty slots, okay. All right, so, okay, these are semaphores, and they keep the producer and consumer operating in proper sequence. In other words, you can't add an item to a filled buffer until the consumer removes at least an item, and the consumer cannot remove an item from an empty buffer, and so has to wait for the producer to put something in there. And so they're nicely synchronized using these two semaphores. Okay. So we don't let a producer insert into a full buffer. We don't let a consumer remove from an empty buffer. Okay. All right. So we do need those two semaphores. Now the buffer, and then this in and out pointers. Okay. Let's assume that it's some sort of circular buffer. They're shared data, right? And the producer will always enter to whatever the in is pointing to, and the consumer will always remove from wherever the out pointer is pointing to. And so the buffer and the in and out pointers are shared. Okay, so we need buffer mutex, okay, to protect the shared data. Okay, and therefore there are critical regions. Okay, so whenever producer or consumer, the code that accesses the buffer and accesses the in and out pointers, those are the critical regions, and we need a mutex there. Okay. Now there's also going to be need for a print mutex, which you'll understand, because both of them are producers and consumers will be printing, and if you have multiple processes printing, to standard out, you're going to get their output interleaved. So, one process is printing a line, but in the middle of that line, the other process decided to print something, and so the output got all interleaved. And so we're going to use a print mutex because we're going to treat standard out as a shared resource. And so we're only going to allow one process to be printing at a time. Okay, so we have a print mutex. Okay, all right. I'm going to show you the program, and then these slides will make sense, because you got to be really careful when you're using semaphores and mutexes. Now the program I'm going to show you is pretty nasty. I mean, it's got a lot of things are going on. Hopefully, I can just kind of explain to you what's going on, and then you can look at it at home. And when we come back next week, we'll talk about it. The program is kind of nasty because it's a C program, and I'm making lots and lots of POSIX calls. And so you're going to see calls to create semaphores and wait and signal, and creating mutexes, lock and unlock. And it's all done with POSIX calls. And the C program then makes all those calls. Okay. So, all right. So here, and this program is just one process. So it forks, or not forks, it spawns two threads, and one thread is the producer, the other thread is the consumer. Now I really haven't, I mean, what threads are. They're all running in the same process. And I really haven't gone over spawning threads yet, but I'll just go ahead and show it to you. And then what we really want to pay attention to are the uses of the semaphores and mutexes. Okay. Okay, so you can see I've got some. Okay, there's an insert item. What's an item? Okay, well, item is just going to be an integer. Okay, and so our buffer is just an array of integers, and we're going to use the in and out pointers. It's a circular buffer, okay, which I'm sure you've done before. Okay, it has a size of 5. And okay, here are 2 mutexes. Here's the buffer mutex to protect the shared buffer resource. It protects the buffer and the in and out pointers. And I mentioned we needed a print mutex, okay? Here are the 2 semaphores. Empty slots available, filled slots available, okay? Now notice these data types. These are the POSIX mutexes and the POSIX semaphores, okay? All right, we're gonna have a producer thread and a consumer thread, okay? And you already saw that they're the insert and remove, okay? Now here's the main, and this program will run for a limited amount of time, okay, 30 seconds or whatever. And during that time, the producers are producing and the consumers are consuming, okay? And the arguments that are passed to this program are how many seconds do you want to run this thing, and how many producers you want, and how many consumers you want. Okay, so this program is set up to handle more than one producer and more than one consumer. Okay, so you can have multiple producers producing items into the buffer and multiple consumers consuming items from the buffer. Okay, and okay, so we're okay, a bunch of you can see I am initializing the buffer mutex, I'm initializing the print mutex, and I'm initializing the semaphores. So I'm initializing the empty slot semaphore to the buffer size because initially all the slots are available, and I'm initializing the filled slots available semaphore to 0 because none of them are filled in the beginning, okay? All right, and then you'll see I print out some things. Here I am creating the producer threads. So for however many producers I wanted, okay, I'm not going to go over this in detail, but basically I'm creating a thread for each of the producers, okay? And each producer has an ID, and each producer will run the producer function. Okay, here's the producer function. Okay, and then create the consumer threads. However many consumers I wanted, I'm going to create a consumer thread, and each consumer thread will run the consumer function. Okay, all right, and this program runs for however many seconds, and when those many seconds are up, the process stops. Okay. Oh, okay. So what is the producer doing? Okay, it runs in infinite loop, and at the start of each loop, it sleeps for a random amount of time. Okay, just to for some variability, it sleeps for 0 to 4 seconds. Okay, and then it produces an item. Okay, so it produces an integer to go into the buffer, okay, and inserts the item, there it is, okay, and then it prints out the fact that it inserted an item, and so you can see here I'm locking the print mutex in order to do the printing, and I'm unlocking it when I'm done, okay, and here's the consumer thread, okay, it then sleeps for a random amount of time, it removes an item, and then it prints out the fact that it removed the item. And so here we're locking the print mutex and we're unlocking the print mutex. Okay. All right, so that's what, so the producer is inserting items, you know, at random times, and the consumer is removing items at random times. Each one sleeps for a random amount of time before it does its work. Okay, well, let's see what insert item is doing. Okay, well, to insert, we have to wait on the empty slots available, okay, in case there are no empty slots. Okay, so we're going to wait on the empty slots available semaphore, and when we unblock, in case the buffer was full, that there were no empty slots, when we finally are able to insert, we lock the buffer mutex. We do the insertion, okay, and then we unlock, okay. And then we have to signal the semaphore that says that there are now filled slots available, okay? And I don't know why, but instead of signal is post, okay? So this is actually signaling the filled slots available semaphore, okay? Now, what's remove item? Okay, this is done by a consumer thread, okay? All right, well, it has to wait on the filled slots available semaphore because, hey, the buffer could be empty, okay? And when it's able to remove an item, it locks the buffer mutex, it removes the item, and then it unlocks, okay? And then it signals the empty slots available because the buffer might have been full, and we have to signal that semaphore so that if the insert item was waiting on it, then the insert item can go ahead and do an insertion. Okay, so this is the program, and I have to say that when I ran this program last night, it got all kinds of errors. Okay, actually, when I compiled this program last night on my Macintosh, okay, I'm going to do a clean and do a compile, and gave me all kinds of warnings. Some in it has been deprecated. Okay, that was when I'm initializing the semaphores, right? Way back up here, where I was initializing the semaphores, it was telling me that, hey, that is deprecated. And in fact, at one time, the semaphores didn't work at all on the Macintosh. So I don't know what the folks at Apple are thinking, but evidently with the later versions of macOS, they changed these POSIX calls. Why would they do that? I don't know. So this program compiles with all kinds of warnings, and the semaphores actually don't work. Okay, so I actually then compiled this thing on Ubuntu. Okay, and so I've got Ubuntu running on my Macintosh using VirtualBox. Okay, in fact, here is Eclipse running with the same program. Okay, and right, so there's the same program, and let me kill this, and okay, terminate, okay, and clear, and now I'm going to run this program with, well, let me show you. Okay, of course, everything is a slightly different place. Okay. I'm going to run this with, for 30 seconds, 4 producers and 5 consumers. Okay, so this is going to look pretty wild, and you're going to see the producers producing and the consumers consuming. Now, when I print out what the consumer is consuming, remember what was being put into the buffer are these integers, I negate it. So it's clear that it is an item being consumed. Okay, so here, yeah, see, when I print out the item, I make it negative just to make it clear in the output. Okay, all right, well, let me run this. And as I said, it's kind of wild. It's going to run for 30 seconds. Okay. And okay. All right, so here are the four producers, and each one of them is producing. And here are the consumers consuming. Okay, so producers produces items in the hundreds. Producer 2 does it in the 200s and so forth. And the consumers, now the consumers consume whatever is next in the queue. And so you can see the consumers are now busily consuming, and they're all running concurrently, but they are synchronized. Okay, and then this thing runs for 30 seconds, and then the program finishes. Okay, all right, so take a look at this program, and next week I'll explain a little bit more about the threads, but at least you can see from this program how we're using the semaphores and how we're using the mutexes. And sure enough, at least on a Unix system, this program will run. This program does not run on the Macintosh. It totally screws up because the semaphores are not working. I need to find out on a Macintosh, okay, obviously they replace the system calls to create the semaphores with some other call, and I need to find out what the Apple folks did. Next week, well, I'll also rewrite this program in C++. Now, C++ has a multi-threading library that hides a lot of these POSIX calls. And so the program doesn't look quite as complicated because we're not doing so many of these POSIX calls. Instead, we're making calls into the C++ multi-threading library, which simplifies a lot of this. Okay. All right, I said I didn't want to run over, and it is now 2:45, so I guess I timed this pretty well. Any questions? Okay. All right, so I will then shut down, and when we meet next week, I will have had my first vaccine shot, which is where I'm going to now to get. Okay. All right. No questions? Then I will then end the meeting. Now you're all working on your process scheduling assignment. So if there are any questions about that, let me know. Don't wait until the last minute to work on that because it is not an easy program to write. Okay. Okay. Stopping sharing, and I'm going to end the meeting. Thank you for coming.
Thanks, Professor. See you.
Okay, you're welcome.